Today's speaker is Elias Most, and Elias got his PhD in 2020 from Goethe University in Frankfurt. And there are people here interested in compact objects, people here interested in gravitational waves, people here interested in accretion flows. Elias works on all of those, and I think his talk today will weave all of them together. So, and a reminder that we'll have our follow-up conversation for anyone who wants to ask more questions than we'll fit in the next hour. We'll have our follow-up conversation today at 2. And with that, Elias, please take it away.
Yeah, thank you, David, for the kind introduction. Although, as you say, I seem to be working on many topics. I'm actually not going to talk about that many topics today. Let me go ahead and start sharing the slides, just so that we can get started. Okay, perfect. So what I thought about for today is, I mean, usually I talk a lot about simulations, but actually for half the talk, I don't want to talk about simulations at all. I want to talk about some more back of the envelope estimates on what we know about how massive neutron stars can be. In the second half of the talk, I want to talk a little bit about kind of the plasma physics interest that I have, sort of as a sideline on what we can learn about novel electromagnetic phenomena in binary neutron star mergers. And so kind of the thing that brings it all together is really this marvelous lab of the compact binary, like the two neutron stars that merge and have all of the dense matter around, and strong magnetic fields, gravitational waves, they curve space and time. So this is really kind of the key lab that I typically focus my work on. And before we can dive into the topics, I just want to give like a brief reminder of all of the different kind of observational channels of the different physics that's going on there. And then once we're done with this, we can really look into what we can actually use observations of binary neutron stars, mainly in terms of gravitational waves, in order to put constraints on what neutron stars are made of and to learn something about new electromagnetic phenomena. And so the idea is when we really look at the late stage evolution of two neutron stars, so I'm not talking about how neutron stars are made, I'm talking about how they die when they are in a binary. So if you have those two neutron stars, they will inspiral each other, and in the process they will really emit gravitational waves, meaning that you lose angular momentum and energy, and at some point they will merge and fuse into one neutron star. And the interesting thing about this is that we have discovered this inspiral gravitational wave signal back for the first time in 2017, and with this signal we got a lot of information on certain properties of the stars. On some of them I will talk today, others I will not touch upon. This is something that Carolyn covered very extensively in her talk, mainly what you can do about, how much you can squeeze the stars, how much you can learn about tidal deformability. But then if you go on in the merger process, you form a very massive, very highly dense hot objects, the hypermassive neutron star. The lifetime will strongly depend on the equation of states, on the nuclear physics that's describing the star, and on the masses. So you can have a star that will live forever, that will become a very strong magnetar. You can have something that collapses right at the merger. But the gravitational waves, they are very interesting because they encode some information on fundamental states of matter. So you could really learn something about, say, the quark-gluon plasma that you might be probing in that scenario. I will not be talking about this today, but if people have questions, we can discuss that in the group chat. The other thing is what happens ultimately if the masses are too high, it will basically at some point collapse and form a black hole disk system. This is very interesting because large parts of these disks become unbound. So this is something, a very neutron-rich matter propagating out. This will undergo our process nucleosynthesis, will generate very nice light curves. And indeed, this is something we've also observed in 2017. And in the later part of the talk, we will use part of the information from those light curves to put constraints on the nuclear properties of the stars, so kind of to go, all the way back in this diagram, to see what comes out at the end. How does it constrain what I put in the beginning? It's also very interesting because you produce all of those heavy elements. Such a very prominent one is gold. We believe that you think you got like the mass of the Earth in gold out of that event, which is more like a side note. And the other thing that will be very interesting for today, but just not what really happened, but that it happened, is that we've seen a short gamma burst. And so since those are typically associated with the formation of a black hole, we certainly can be more or less sure that the system collapsed to a black hole at some point. And that will put very strong limits on how massive neutron stars can be. And finally, for the second part of the talk, there's one phenomenon we have not yet observed. It's also very challenging to observe, but in principle, because neutron stars have very strong magnetic fields, you would also expect to get some sort of emission from right before the merger. And that's something that I will address in the second part. We have a specific model there. All the hair of the neutron stars, you can see, gets all tangled up. It can reconnect. You can get flares propagating from the system, and those might tell you something about the spin and magnetic field topologies of the stars before the merger. And so with that, I want to directly dive in and not talk too much about the merger itself, but I want to ask a very fundamental question. If you've never heard about a neutron star, you could ask, what does a neutron star look like? And if you're really impolite, you might ask, how heavy is a neutron star? Or better say, you can ask, how massive can neutron stars be at most? And so for that, just to kind of get some idea, neutron stars in principle are covered just in terms of their composition. So if you want to ask what does a neutron star look like, you basically just have to ask what is a neutron star made of, and also what's the governing theory of gravity. But for all simple purposes, we assume that's general relativity. And then once you have that, you can kind of compute how big is the neutron star for a given mass. And the way this works is that because you have these super extreme densities inside a neutron star beyond nuclear saturation, so you really start, in principle, you could start deconfining nucleons into their core constituents at the center. So this will really govern what my star looks like. And the main feature here that, if you've never seen this, this all might sound a bit opaque, but the main feature really is the more exotic you get, the more problematic things get. So if you, for example, produce strange quark constituents inside a neutron star, that strictly limits how massive they can be. And so there's sort of like a competition in between having more exotic degrees of freedom and going to high mass. And so eventually, if we can answer the question astrophysically, how massive can neutron stars be, that's very constraining to the exotic degrees of freedom that a neutron star can have. So just if you want some background motivation of why we should be asking the question in the first place. Otherwise, it's interesting also, even if it wasn't fun. But now what you have to do is, once you have a composition in terms of equation of state, what you can do is you need basically the pressure as a function of energy density. You can put that into the fancy version of the stellar structure equations, and that gives you what a non-spinning spherically symmetric star would look like. Once you do this, you can compute a lot of mass radius curves. This is what people typically showed. And I think we got a lot of them to see in Carolyn's talk, who told you how we can actually learn how big neutron stars are. But today I'm only talking about how massive they can be. And so the two kind of limits we have on the mass are, one, that observationally, we don't really see neutron stars with less than 1 solar masses. And there are some simulations of Corcolex supernova that basically say that's also very difficult to achieve. So maybe this is kind of the lower limit that you have to think of. And then the other thing is, we do have observations that indicate that 2 solar masses are feasible. And so we somehow have to get up there, but we don't know how high we in principle have to go up with those curves. And so today we really just focus on this upper end and try to answer, like, where do the curves terminate, or better say, how massive can neutron stars be? Of course, you can do this from a theoretical point of view, but you can also ask, what do we know observationally? And there are basically the two kind of observations of the most massive neutron stars are one by Antoniadis et al. And one by Cromarty, where what you typically do, measuring a neutron star is you cannot put that on cosmic scale, so that's not so simple. But what you can do is, if the neutron star is in a compact binary and say it has a white dwarf companion or another neutron star companion, you can try to measure sort of the mass of the companion and then try to get what the mass of the neutron star is. And the main thing that's used there is something called relativistic Shapiro delay. So this is when you have pulsation from the neutron star, basically crossing, in the case of Cromarty, crossing the white dwarf. It will receive a time delay, and the time delay is proportional to the logarithm of the mass. So from that, you can kind of do a differential measurement of the white dwarf. You combine that with the orbital period by Kepler's law, and it tells you how massive the neutron star is, just if you want some background on how that works. But for the practical purposes, what this is telling us is that you basically have neutron stars with masses of at least 2 solar masses, and that's really constraining in terms of the nuclear physics that I was mentioning. In terms of the hyperons that you can get, it's very difficult. In terms of quarks, this can be really difficult. And the latest contester really is saying we might push it up to like 2.1, which is quite interesting. And so another method that you can do apart from direct observations, this is something that has been proposed in the aftermath of 1708-17, is you can use gravitational wave events, and especially multi-messenger gravitational wave events, in order to derive constraints on nuclear matter in this way. This is something that I have some works on. I thought I share this because this discussion became really relevant last year when people were asking, there was a mysterious gravitational wave event I'm going to talk about in terms of where it was unclear if you have a neutron star, you don't have a neutron star in terms of the masses that you have. And so you can basically use that to constrain, is it really feasible to have neutron stars in high mass systems? But we'll get to that. But before we go there, I mean, we basically have to look at something like rotating neutron stars 101. So what's the basic things in terms of stability of neutron stars that we need to understand? And so if you just plot the same mass radius curve for one fixed equation of state, so you pick one of those curves and you plot them in terms of their central energy density, in terms of the mass that they have, the curve looks a bit different. It will have a maximum. And this is where the maximum mass is, and everything to the right of this is basically unstable. If you were to form that in nature, it would immediately collapse into a black hole. So really the only physical branch of this is like the left side, everything to the right would collapse. Now, the interesting thing is, I mean, you know, non-rotating neutron stars are cool, but most neutron stars are rotating because that's what we see in pulsars. We see really spinning neutron stars. And if you have very high spins, neutron stars can support much more mass. And in fact, it turns out they can support about 20% more mass. That's something that you can find if you solve the equations for relativistic stellar structure of rotating equilibria. For many, many equations of state, and you just fit this, you get something like this 20%. It's a bit contested, and I will say something about it later, but that's kind of the face value that we should have in mind. And so what will then happen is you can basically tune up the rotation up to the point where you go to the stability line. This is called the Keplerian limit. At that point, you really start shedding mass at the equator of the star. You're basically spinning it too fast. And so the rotation velocity would exceed the speed of light, essentially. And so that basically telling you rotating stars can support more mass, about 20% more, but not more, otherwise they would become unstable. This is still not the full story, because what you actually get in a neutron star merger, so this hypermassive object that was on one of the earlier slides, where, you know, after the collapse you had this super dense thing that was oscillating, that would actually turn out to be differentially rotating. And very counterintuitively, it turns out that it has a uniformly rotating core, then the outer layers rotate faster, and then it has a Keplerian fall off. So this is kind of the rotation profile as a function of radius, what I'm showing here. And what you can then do is you can say, well, where do my rotating configurations live? And the interesting thing, rotating stars can support even more mass. And so they go up above the Keplerian line, and you populate all the entire rest of the parameter space. And this will, where exactly you lie will essentially depend on the rotation law, so on how this curve looks like, but more or less you end up at higher mass. And you can then ask, you know, how does that translate? Can you also derive like the 20% criterion for differentially rotating stars? The answer is sort of yes, but it depends. We tried to do something in 2017, but we picked sort of the wrong rotation law because it's relativity, it's complicated. But if you simplify things, you can support a little bit more. But then it's not really clear at which point they will collapse. So you basically have to modify the criterion on where they become unstable. Because the thing that I probably did not point out clearly enough is one thing that we will be talking a lot about is the point at which a star is too massive to support itself under the pull of gravity. And in this diagram, this is basically governed by this black line here. So as soon as you start crossing the black line, as soon as your density at the center, because that's really the central density, is becoming more massive, the star will become unstable to the collapse. And so really, as soon as you sort of move to the right of the diagram, you cross the line, your neutron star ends to exist, and you form a black hole. And determining the point where this happens will really be crucial in terms of telling us when we will form the black hole and what kind of upper limit on the mass descent. And so what we can now do is we can say, okay, we have all of those definitions. So let's apply this to 170817. And there, the interesting thing was that we did observe a short gamma ray burst, and in most models, this really coincides with black hole formation because you somehow get a jet from this, and we have observed a structured jet now a few years later, and with actual confidence that it was a structured jet. And to collimate this, you really need the black hole. So you kind of can be very sure that we did form a black hole. So at some point, we did cross the black line that I was just showing. So we can use that. And so the picture that we will be discussing here is the following. 170817 starts out as a differentially rotating neutron star. So it kind of has to start up somewhere in the salmon region. And then what will happen is it will basically spin down. This is done via magnetic braking. This is done by gravitational wave emission. So what will happen essentially is, because you can do a timescale estimate and you can kind of find this takes a bit longer than just quickly collapsing as a differentially rotating star. So if you do the timescales, you find that you actually collapse as a uniformly rotating star. So you simply estimate how long does it take to remove differential rotation. You see the collapse should happen as closely as a uniformly rotating star. So you will cross somewhere down here in the green region. And the interesting thing is, if you come close to M max, we just know what M max is because it's 20% more than MTOV, and so you can immediately infer what the maximum mass of the neutron star is. But we'll walk through this in a bit more detail.
Can I ask a question about this diagram?
Sure, let me just go back this way. Yeah.
So when you consider different equations of state that, that give you different M max, is it because that separating line is moving in this diagram, or is it because different equations of state give you a different rho C for the same M?
Right. So the interesting thing is they do give different rho C for the same M. And so in this diagram, in absolute terms, this upper line is moving up or down, and it's also moving left or right. But the interesting property that turns out is that the ratio of M max to MTOV is pretty much insensitive to the equation of state. That's a property of GR. It's not a property of nuclear matter, or at least within the error ranges of nuclear matter, this is roughly a constant. And this is where the whole thing relies upon, basically, because you say that M max is always 20% more than MTOV, or about 20%. And so as soon as you get M max, you know what MTOV is, independent of the equation of state. And
what does the TOV stand for?
That's the maximum mass of a non-rotating star. That's named after Tolman, Oppenheimer, and Volkov, who came up with the structure equations for GR. Sorry for the confusion there. So this is really the non-rotating sequence down there is the black line, and then the green region is all the uniform sequences. Right. And so we basically use that universal property to put a constraint.
Can I also ask a question?
Sure.
Before we move on? When you're saying that path 1 is more likely than path 2, that relies on the EM counterpart. How sensitive is that? I mean, how unlikely is path 2?
So what you have is you do have a time delay between the short gamma ray burst and the merger, like gravitational wave signal, where it terminates, of about 1.7 seconds. And you can do an estimate based on magnetic braking timescale. So if you put like reasonable values for the field strength that we know from simulations, because there's some amplification in the merger process, but let's say you put an order of magnitude estimate for that, then you find that the braking timescale due to the magnetic fields is about 100 milliseconds. And so basically you say, well, okay, if the short gamma ray burst happens so much later, but maybe the black hole accretion flows don't take a full second to push you there, you would be uniformly rotating at the collapse. You would not basically collapse immediately, because if you collapse as 2, then likely what would drive the collapse would be gravitational wave emission in the post-merger, because that removes a lot of angular momentum when you still have this bar shape, and now you're still differentially rotating. If you collapse later, you're likely close to uniform rotation. It's a very good question, actually.
Yeah, I guess I'm just wondering how, if there are any reasonable scenarios that lead to path 2, or if that's completely,
I think for different masses, you will have path 2. I think the thing is where we really got lucky is that the total masses were just in the range where this likely did not happen, just because of the delay that we have observed. If we hadn't observed that, then we wouldn't know. If you think about having a higher mass merger that's close to like prompt collapse or so, I mean, you have 2. You don't have 1. I think there's a very special property. Also, if you look in terms of the mass ejector that we will use later on, I mean, you got a lot of mass ejector. Also, you got some mass ejector from that likely come from a hypermassive neutron star. So this tells you that the hypermassive neutron star at least must have been around for a few hundred milliseconds, even if you take that into account.
Thanks.
And so that's exactly the next point, because we do have this additional information. If we look at the light curves from the kilonova, and you can do some radiative transfer modeling, you kind of get an idea of how much mass was ejected from the system. And there are 2 components. There's a blue component and the red component. And the blue component is what is basically, from a simulation point, associated with what is coming from the hypermassive neutron star. The reason is the blue component has very high electron fraction, and in order to get this, you need a lot of neutrino radiation, and that you more likely, from simulation point of view, have just right above the polar region, or in the polar region above the core. So you basically can say, because we're seeing some of that, the hypermassive neutron star must have been around, but we don't see the same amount that we see in red ejecta, and so it cannot have been around for too long. So this gives you some kind of hand-wavy bound on it hasn't lived long enough to become uniformly rotating, but it hasn't lived long enough so that it didn't collapse. And then what we what we can do is we can do a very quick back of the envelope estimate, just like putting all of what I just said together. So you take the gravitational wave signal, it tells you what the total binary mass is. You look at simulations, and simulations tell you how massive is the core, because if you look at the simulation picture, you sort of have at the center this in red, the hypermassive neutron star. That's the thing that's actually going to collapse. So this is what we want to constrain the mass of. And simulations give you something about the mass fractions, about 95% of the total mass that you put in. This is just what you get as a reasonable range. And then you say, well, there's certain mass that is being ejected from this core. This is where the blue ejecta, and those I have to subtract from that mass, because during the lifetime, those will fly out. And then I have to, in principle, also account for gravitational binding energy, because in a gravitational bound system will have less mass than an unbound system. It's just if you count the number of particles is not the same as if you were to assign actually mass to them, because there's binding energy. And then you do this, you say, well, we translate this in a simple equation. We say we started out somewhere as a differential rotating star, but only the core was what essentially collapsed. But before it collapsed, it ejected some mass. This gives you a relation that looks actually very simple. And under the assumptions I was discussing, this means that you collapse somewhere close to Mmax. And for simplicity, we just say you collapsed at Mmax. I'm going to relax that later, but for now, we just say, you collapse close to the maximum mass. You get that equation. And then using this universal relation where we say that Mmax is always 20% more for the maximally uniformly rotating star, and for a non-rotating star, we can actually solve what is the mass of the non-rotating star just by plugging in numbers. And this is what we did back in 2017, and also what other groups did. And remarkably, you come out with something that is reasonable in the light of current observations. I think we came up back then with like 2.16 plus minus 0.15. So the upper limit that people have found is consistently about 2.3 solar masses. You really have to look at the upper limit as kind of the constraining factor. So this would say, no non-rotating neutron star can be heavier than 2.3. Why is it something that we have to care about right now? If this was done in 2017, I mean, or in general, I mean, sure, it constrains the nuclear physics, but why is that something interesting to think about? And this is because we did have a gravitational wave event of a 23 solar mass black hole with a 2.6 solar mass companion. And we don't know from the gravitational wave signal what the companion was. Could have been a black hole, could have been a neutron star, could have been something really exotic, some dark matter, primordial black hole, whatnot. In fact, if you were checking out the archive, like shortly after the fact, and you look at the number, this was like number 35. I think there were like 50 papers popping up, all claiming that the thing could have anisotropic pressures, could have exotic matter, could have been modified gravity, or something else. And the thing is, you don't need to go that far. In fact, if you just think about maximum masses of neutron stars, you can make a very quick determination if it was a neutron star or a black hole, even without making some other assumptions. And so the question is really now what goes wrong if you have a neutron star. So I mean, this would be the simplest picture. Why not have a black hole? But that's sort of a little bit disfavored, because if you look at core collapse supernova, getting black holes below 5 solar masses is hard. It's not impossible, but it's difficult. And there have been many papers in the literature by now showing what you have to change to do this. But if you have a neutron star, does it even make sense in the light of what I just said? Because the main sort of issue is that if we believe that a neutron star can at most have 2.3 solar masses, how can you reconcile this with having 2.6? That just doesn't seem to match, unless what I was saying was just too crude of an estimate to make sense. And so the thing is now, however, if you believe that sort of 2.3 is a good number, you can still bump this up if you add that the stars can be spinning. Because we said it's 20% more. If you add 20%, you get to 2.8. And so that kind of makes sense. And so kind of the message that I want to put is, if you really believe this thing was a neutron star, it must have been very rapidly spinning, with all of the drawbacks that might entail. And so what you can then do is you can say, well, how much is massive spin in absolute units, just that we get some idea. And there's some this is kind of the follow-up to the neutron star properties. You can look again into rotating equilibria, and you can ask, is there a correlation between how fast I can spin and how big a non-rotating neutron star is at the most massive configuration? The answer is sort of yes. And the value you can remember there is something like 0.7, which is interesting, because that's basically telling you that neutron stars are not like black holes. They cannot go to maximum spin where the spin parameter would go to 1, just like for the black hole where you go to the extremal case, but this is limited before to like 0.7, which also means that any black hole formed by a collapsing neutron star will at most have like 0.7 in spin, just if you want to keep a number at the back of your mind. And then what you can do is you can say, well, let's combine this. Let's ask really, how much spin do I need to explain this 1908-14 observation? And there, what you have to use, you don't just use the 20% value, but it's actually a relation that sensitively depends on spin. So you can even, from the equilibria, given a certain amount of spin, what's the maximum mass I can support with that spin? This is the black curve showing here, goes from like 1 to 20%. And then we can just overlay this with the mass range that you have for 1908-14. And then what this is telling you is that you can basically ask the simple question, like, if I can support at most 20% more, but the lower error bound on 1908-14 is 2.5, I can just divide it by 1.2, and I get that my most massive neutron star must at least be 2.08, right? That's the first conclusion. So if you actually had a rotating neutron star in there, this sets a lower bound on the maximum mass, which is interesting because that's the first time that you can actually set a lower bound. Again, you have to believe it's a neutron star, which will turn out to be a little bit more complicated, but that's roughly the idea. The other thing is you can ask, well, it's great that you can do this, but what's the minimum amount of spin that I need in order to explain this if I believe that 2.3 is a good number? Because again, if I add a certain amount of spin, I can support more mass. If I want to go from 2.3 to 2.5, I need a certain amount of minimal spin. It turns out that this is 0.5. And so what that means in practice is, if you really believe that this thing contained a neutron star, it must not only have been spinning, it must have been spinning with a spin period of less than 1 millisecond. So that would have been the fastest neutron star we have ever seen, faster than any pulsar observation, which pushes this thing to a really extreme sort of place in the parameter space. And so the obvious question then is, okay, how sensible, because it all hinges on the assumption that the maximum mass is limited to 2.3 based on 1708-17. So the question is kind of how sensible is that? There's a recent work that we've done and that got published in, I think, last month, where we basically asked the question, like, how far can you push it? How far can we relax the assumptions that went into the simple back of the envelope estimate? And there are basically two questions that we need to ask. One of them is, how efficient is gravitational wave emission? This sort of hinges on the point that Carolyn was making, was like, do I lose enough gravitational, do I lose enough angular momentum? Or better say, the question for us is, can I lose even more angular momentum? Because that turns out to be beneficial if you want to have higher masses. On the other hand, how consistent do I have to be with the kilonova afterglow? Because after all, I mean, there are errors in the modeling. It might be that the numbers are off. And so, how much does that influence the result that I'm getting? And so the main thing that actually turns out to govern the error is really if you collapse close to max, so you would collapse further down. So if you assume that somehow you would be able to radiate even more angular momentum, so you would have very, very efficient angular momentum transport, and you don't collapse where the star position is, but somehow your red path would bend further down and it would collapse, somewhere here in the middle, or here where the orange shape is, then that would significantly change the amount of maximum mass that you get, because remember, the maximum mass is inversely proportional to kind of this difference in mass that you have to the baseline. So the further you go down, the higher your maximum mass will have to be in the end, that you infer from that method. And so once you assume that you're radiating more angular momentum and more energy in terms of gravitational waves, this immediately relaxes the bound. However, you cannot relax it fully. I mean, that also doesn't work, because otherwise you never form a black hole and you're inconsistent with the short gamma reversed. And I don't want to bother you with, the complicated model, because it would probably, instead of just filling like the small part of the slide, it would fill the entire slide. But essentially these pictures show you what this does. On the left, you see the mass lost in gravitational waves. It's the parameter that we tune now. On the right, you see the mass ejecta that are consistent then with the observation. The observational band here is in green. So what you can basically do is we said, okay, let's not care about getting the right ejecta, but let's care about getting gravitational mass losses that are consistent with numerical simulations. Because numerical simulations give you some idea on how much angular momentum and gravitational mass you can lose in the early post-merger. This is where the neutron star is not axisymmetric, it's bar-shaped, so it's really strongly emitting gravitational waves. Actually, if you look at the numbers, it's emitting 0.1 or 0.15 solar masses. That's not insignificant compared to the numbers for the maximum mass, for the error on the maximum mass estimate that we're talking about. So really, you have to account for this. And the thing that we find is, if you try to break this, and you really say, let's say, what happens if I had 2.4 or even 2.5? So what if the 1908-14 event contained a non-spinning neutron star? You really break it hard both on the gravitational wave emission and on the ejected mass. And then you can say, okay, let's push it even harder. Maybe I can at least make one consistent. And we found in principle, if you don't care about, how much energy you can lose in the post-merger. If you say I could arbitrarily efficiently dissipate energy and dissipate angular momentum, you can still be consistent with the counterpart for 2.4, but you have no chance of getting the mass ejector right for 2.5. And so that would tell you that even, you know, if you want to raise that limit, you would still need rapid rotation to some degree in order to explain the 1908-14. And so sort of that puts the two observations kind of at odds. And what actually is telling you is that maybe, you know, you don't have a neutron star in 1914. That would be my personal conclusion. But I'm happy to discuss this further in the discussion session. And so kind of the summary, if you want some takeaway message for this first part, is if you look at 1708-17 and you look somewhat at the stellar structure and general relativity and some universal properties of the equation of state, then you see that the neutron stars can at most have 2.3 solar masses. In doing this, you make certain assumptions. The assumptions are mainly on how efficiently you can lose angular momentum and gravitational energy, binding energy. And this tells you if you relax those assumptions in a meaningful way, you can push it to at most 2.4. You cannot push it to 2.5. And so this means for the 1908-14 event, where you had an object with on average 2.6 and the lower bound is 2.5, if this was a neutron star, it was likely rapidly spinning. However, most likely you would say, well, if it's also complicated, it might also have been a black hole at merger, because you could easily think about a situation where you form a massive neutron star, the neutron star collapses due to accretion, say, and there were some scenarios proposed for this. So you form the neutron star early on in its life, it collapses to a black hole, the black hole accretes more mass, and then at merger you have a more massive black hole than that threshold. But it likely is telling you that a neutron star is not a good option here. One of the caveats that I did not talk about, I mean, there's basically, if you start to include other degrees of freedom, such as quarks, or if you think that the hypermassive neutron star formed after the merger is very hot, then there might be additional error budgets kind of going into that estimate. So the 2.4, even a 2.4 is not set in stone at the moment. But the thing is, there will be an upper limit, and it will likely be less than 2.5. That's kind of the key takeaway message. I mean, if there are any more questions to that part now, I guess would be a good time, because then I would go over and talk about this precursor phenomenon. Okay, I mean, we can save the questions for later. So, you know, let's look at, you know, some simulations, because as David was pointing out initially, I mean, I'm actually doing a lot of simulations. I'm not doing too much of those back of the envelope estimates, or even, you know, working on nuclear structure. And so one of the things that I found very interesting is, like, if there's another counterpart apart from those that I already mentioned. And the main idea is really, because neutron stars have very strong magnetic fields, in principle, the interaction of the magnetic fields, a non-trivial interaction of the magnetic fields, should produce some sort of event right before the merger happens. So, you know, kind of the artistic picture is actually a simulation picture. You should see some sort of flaring type event right before the neutron stars merge. If you do simple back of the envelope estimates, one of them is by Dong Lai, who proposed that it should be of the order of 10 to the 42 ergs per second, would put it in the same range energetically as a fast radio burst. There's some caveats of why this is not a good fast radio burst model, but we can save them for later. But so the interesting thing is, in principle, you would expect similar phenomena either in the radio band or in the X-ray band. And so the way that this works, just to take another step back to our neutron star 101 part, neutron stars can spin very rapidly. I mean, they might not be spinning with less than a millisecond, but the fastest one is 1.4 milliseconds. They can have very strong magnetic fields. This is what you essentially get from pulsar spin down. And this tells you that the field strength in the neutron star can reach about 10 to the 12. And there are special neutron stars, magnetars, that, for example, could be the long-lived remnant of a neutron star collision for a low mass binary. They can reach 10 to the 15 gaps. So you have a lot of magnetic field, a lot of energy in that electromagnetic sector around. And sort of, if you can liberate part of that, that would give you a very nice counterpart. And so what is interesting about those neutron stars, or one of the reasons why we can actually see any emission from them, is because they're so rapidly spinning with so strong magnetic fields that what will happen is you will produce a voltage gap at the surface of the neutron star. And the voltage gap is basically, you need magnetic field strength of more than 10 to the 11 Gauss, I think. What happens then is you accelerate charged particles from the surface in the voltage gap, because those, it's like, look at the little electron here, those move on curved field lines. And because they move on curved field lines, you get something that looks like synchrotron radiation. So you get these gammas. And then when the gammas interact with the field lines, they can again produce electron-positron pairs. And so what you get is you trigger a pair cascade in the vicinity of the neutron star that's basically immediately filling up the entire surrounding. And that means that the neutron star doesn't live in vacuum if it's rapidly spinning or moderately spinning and strongly magnetized, but it really has a conducting electron-positron plasma, pair plasma around it. And that plasma is very interesting because it leads to certain phenomena. For example, if you have a rotating neutron star with, let's say, like a dipolar magnetic field, then there will be a point where uniform rotation would give you a rotation speed larger than the speed of light. And at that point, your field lines would have to open up. You can imagine this, although this is a very bad analogy, but you can think of this as kind of the field lines getting some sort of inertia. And they cannot move faster than the speed of light. In practice, it's just a matter of currents flying around, which is if you want to have a simple picture for that. And then what those can do, there's a very interesting phenomenon that we will rely on. It's a phenomenon of reconnection. I will also use that opportunity to advertise our new plasma learning seminar that will start this week with a lecture by 11. There will be one by Jim on reconnection, so he will tell you all about it. For the purpose of this talk, we just need basically very simple facts. If you look at this nice animation that I got from Wikipedia this morning, what you see is, you see that oppositely aligned field lines, so the red ones and the blue ones, in the presence of a current sheet, so there's a current going into the plane, just right where the arrow tails are, will reconnect simply because the energetic configuration of them kind of doing this X-shaped reconnection is more favorable than staying separated. And that's interesting because if something is energetically more favorable, you're going to liberate energy, and this energy is then able to do particle acceleration. This will ultimately lead to the production of coherent radio emission or X-ray. And so this is really what can make your counterpart that your telescopes can see. So looking at reconnection in such a binary is very interesting for that point. And one more thing that we will exploit is that actually this reconnection or dissipation phenomena in this current sheet is very special. This is very unlike dissipation that you have, let's say, for shear flows, in that there's a specific limit that you approach. It's called the plasmoid limit. It's a very nice animation or very nice picture from Bart Ruperta, where you can see that at some point you form these little magnetic islands because the current sheet becomes plasmoid unstable. It actually turns out that these islands are quite crucial because they can also produce radio emission. So you get like a secondary emission channel that can produce an observable signal. And we will see that this will copiously happen in a binary neutron star, which is really cool because we were the first ones to actually see that in such a simulation. And so if you want to translate that back to the pulsar, where is your current sheet? Well, as I said, the field lines have to open up at the light cylinder. And so you see that there are like very large current sheets around. And one of the recent works by Sasha Filipov was to show that these current sheets are Turing mode unstable. So they form these little plasmoids. And when the plasmoids merge, right, for the magnetic field strength that you find in a pulsar, they produce radio waves, and they just happen to lie in the radio band if your magnetic field strength is about 10 to the 8 Gauss in the current sheet. And so that's really, really interesting because it gives you, it's not the main mechanism of how to explain pulsar radiation, but gives you an additional phenomenon, additional mechanism in the current sheet to produce radio emission. This is what we will see later on in the binary. And just a little note here, I don't want to go into too much details. Basically, when you assume that you have a force-free plasma, there's a specific set of equations you need to solve. You need to solve Maxwell with a certain prescription for how this is done. We can talk about the details later. For purposes now, it doesn't matter. One of the things I have to point out, however, because we will look at some of the movies that I made for this, is because I have a training in numerical relativity, I thought just looking at the rotating star is too boring. So instead of rotating the star, I will rotate the entire space-time around the star. So in all movies I will be showing, it will actually be the things around the stars that are counterspinning and not the star itself. And there's a very fancy way in the GR formalism to make this work, but that doesn't matter for now. It's just, we'll look at one particular movie where that actually is very beneficial to do. And so one of the things that I also want to point out, if you want to do any such simulations, you need a numerical code. This is, the thing that I've been developing for some time. It's still not 100% ready, but in principle, I have a code to do GR MHD simulations in dynamical space-time, doing all of these fancy electrodynamics, resistive MHD, and also with adaptive mesh refinement. And the adaptive mesh refinement point is really crucial because these phenomena have a very certain scale separation. So actually, let's skip that. That is not relevant, but let's look at this one here. So this is looking at the current sheet in a pulsar, but looking in a very specific pulsar. So what you do is you take a neutron star, you shake the field lines at the top of the neutron star. This is based on work that Yaji-Wan at Flatiron has done. And what happens then is you get an alpha wave propagating out. This is what you see here. This is like just a think of it simply as a wave along the field lines. And what happens is this alpha wave will become nonlinear, it will trigger the plasmoid formation. But as you can see in the zoom in, plasmoid formation happens on a much smaller scale than the scale of the wave or the scale of the star. And so what you need to do numerically is you need to have enough resolution to capture those dynamics, but still be able to resolve the global scales. And so having an algorithm where you can have this set of nested grids that adaptively follow your structures is kind of the key feature to enable this. And this is in the project I will not be talking about today, but we could effectively use that to do one of the highest resolution simulations of current sheet formation in 3D. And then you can really see how in 3 dimensions, this plasmoid formation happens in in basically multiple dimensions, not just in one. That's something I might be following up on at a different point. And so going back to the binary, what's the actual scenario that we're considering? If we think about the picture that we had earlier, you have the 2 stars, you have magnetic fields pointing up, you have magnetic fields pointing down. We look at the very specific configuration, because what can happen then is that the field lines that go from one star into the other star begin to connect. And what you can basically have then is you can have a closed loop. And now it gets really interesting, because even in an irrotational system, if you look in terms of, if you follow the motion of the stars, in the co-rotational frame, they have an effective spin. But for the present purposes, just think of one of the stars as spinning. At that point, the magnetic fields will behave like rubber bands. If you put that between your fingers and on one side, you start to twist the rubber band, you transfer rotational energy from the twisting motion into the rubber band. And so the idea will be, can we tap into the energy budget from the orbit or the rotational energy budget from the star? Can we temporarily store this by twisting the field lines in the magnetosphere? And then when we have this funny reconnection phenomenon happening, you can liberate part of the energy and you get this burst out. So that's kind of the main mechanism here. It's quite interesting because it's the same idea as you have in a pulsed laser, where you say, continuous emission doesn't give me enough power, but if I can somehow store that energy and then release it over a short amount of time, I get temporarily a higher power, and that might make it detectable. So it's kind of the basic idea that we're using here for the neutron star binary. And then I'm going to just first show you like a proof of principle of that this is working. So we're going to see here in black the neutron stars. These are not black holes, these are neutron stars. So the color is kind of a very poor choice in hindsight. But what you're going to see is you're going to see the connecting flux tube here. So this is the connecting magnetic field loop. The left star has a field pointing downwards, the right star has a field pointing upwards. In a simple case, there is a relative spin difference so that the right star will be spinning. And then what you see in color is the out of plane magnetic field. This encodes the twist. So whenever you see some color, this is a twist building up, right? And so now we can look at the movie of what is actually happening. So you see, as I'm twisting the star, I'm kind of putting more energy into the magnetosphere. And then at some point, I over twist the configuration just as the rubber band would break. In the same way, the magnetic field lines reconnect and you get this flare that is propagating out. This will make your observable signal. And then in the aftermath of the flare, you see that there's a trailing current. You see these little plops, and those are the plasmoids I was talking about. And this will essentially give you 2 types of mechanisms for radio emission, also X-ray emission in the system. One's coming from those little islands, and one's coming from this big kind of pancake thing that is leaving the merger site.
Well, can I ask, so the
Sure.
magnetic fields that are connecting the 2 neutron stars, your notion is just that initially each neutron star forms with its own magnetosphere, and then as they come closer together because of gravitational radiation, you will that will lead to
exactly. I mean, that's exactly the point. So in order for this to happen, the stars have to be, let's say, in enough of a close contact. Because when you think in terms of light cylinders, so you associate a length scale via the speed of light with each of the rotational periods of the stars, then they basically have to be in each light cylinder. Otherwise, they would just disconnect. Like one star would be spinning, the other star would be spinning, but there would be no relative twist building up, because the twist is actually mediated physically by an alpha wave, so by like a wave propagating along the field lines. And so the travel time between this has to be short enough, otherwise you don't get a twist. That's a very good point. Yes. So this is a phenomenon that by construction would only work on the last orbits, not beforehand. Even if it was to work, not apart from that, if you think that the dipole has a certain radial fall off, the energy that you can store in the field also falls off. So the thing would basically not be detectable for this.
Provided each neutron stars, it's self-magnetized, and you bring them together, then it's natural to form these.
Exactly. There are even some estimates. I mean, this crucially hinges on the fact that the stars are still active in some sense, because old stars, they happen to spin down, and also the magnetic field is going, well, old stars, if they're recycled, they spin up, but in general, the magnetic field is going to decay. At some point, you can no longer trigger pair creation. But the interesting thing that turns out is because the orbital motion is fast enough, that can trigger pair creation again. So even though the rotation of the star might not, the orbital motion will take care of this. There were some nice estimates out there in the literature last year or so. And then what you can look at, if you look at just the profile of such a flare, this is really interesting because it kind of boosts the emission that you had initially by almost a factor of 100, if you want to compare that, compared to just moving a star around. This is literally because you can store the energy in the magnetosphere and then just release it over a shorter time. It's really like the pulse laser. You're just pulsing the emission coming from the binary. And then when you look at this, you have these two distinct type of emission channels, one coming from the pancake shape of the stars, because as this stuff is propagating out, it's becoming thinner and thinner, and it's like a homogeneous shock front propagating against the ambient medium. And there's some models for this in the context of magnetar. Models for fast radio bursts that you can basically jump on and recycle them. You can also look at the merger of plasmoids, and if you look at the field strength that you have, you find that the kind of this pancake has about one order more luminosity than is contained in the dissipation of the plasmoids. But I get to that in some more detail in the next minutes. But the question that I want to ask first, I mean, the movie that we were seeing and the first case that we studied back in 2020 was a very simple case. We assumed that the fields were aligned, they were of equal strength, and this gave this really nice picture that I was just showing. So before I continue, I want to convince you, this is work that is still in progress, that this phenomena actually happens quite generally. So even if the magnetic field are misaligned for the two stars, because in general, the fields are not aligned with the rotational axis. Otherwise, we wouldn't see any pulsar rotation because there would be no spin down. And so we would not see any emission from pulsar. So realistically, you assume that there's sort of a misalignment. And you can see, for example, for 60-degree or 90-degree misalignment, you still get flaring events. And I just indicated the flares with the arrows. You can just have a look that the same mechanism will still work, and it will still periodically produce flares being emitted from the inspiralling binary. You can also ask, how robust is this if I change my field strength? For example, if I say one of the stars has 10 times of a weaker field strength, here we look at the configuration where in the top where two of the stars are misaligned, so they're both misaligned by 60 degrees, then they're spinning around with some low spin. And what will happen is that the flaring is most prominent, of course, in the equal field strength, because equal field strength kind of pushes this to the polar region. So there you can build up really large flares. If what happens is that the field strength is different, then in terms of the rubber band, you have to think of as the rubber band becoming thinner once you go to the lower magnetized star. So as you twist the field lines, the twist will happen much closer to the stellar surface, and that limits the amount of twist you can store and the amount of flaring you can get. And you see that you get like very small flares, but you still get flares. So that's kind of a very generic thing that is going on. You can also ask, I mean, that's more of a recent question, but you can also ask, there was an observation from the NISA mission that indicated that the neutron stars don't have dipolar fields close to the surface, but instead there was some multipolar substructure, and they get that by doing hotspot modeling. So instead of just getting the spot that you would get for a dipole, you also get this crescent shape. And if you do this, we just said, okay, why not try this out? There's some formulas for quadrupolar, quadrudipolar field configurations where, similar to this crescent shape, you can basically produce a small quadrupolar component close to the star. And that would be important because as the stars come closer together, they would start to feel the non-dipolar components. So really close to the merger, this would make a big difference. And so we also checked that. So we basically combine a neutron star that is a pure dipole with one that has the quadrupolar component. And now the really interesting thing is you can basically do this reconnection phenomenon, not just with the dipolar part, but also with the quadrupolar part. So you can get double flaring events. And so what that would mean is, physically, as the stars come closer together, this phenomenon is enhanced just because you have like two different hemispheres of the stars that you can suddenly flare with. which is interesting. But it's more like a side note, as you know, if really neutron stars have significant non-dipolar topologies, that would actually be quite beneficial. But so now for the final part, I want to kind of, I hope I've convinced you that this is like a good thing to do, right? But we still have to sort of estimate what's the amount of energy that is generally available to drive any electromagnetic phenomenon associated with this. Because, I mean, our eyes don't really see pure electromagnetic energy. They see energy in certain wavelength. And so whatever I show you in terms of flares going out or pointing flux going out might not be the right wavelength for any telescope to pick up. And so you need some conversion mechanism to go from having electromagnetic energy to having something, say, in the radio band or the X-ray. And one of these things are those plasmoids and the merger of those plasmoids, because they're copiously around. And in order to estimate how much energy is lost there, we have to do a little bit of a accounting, very similar to the quick estimate I was doing for the maximum mass. Because what you can do is you have to estimate the amount of energy that is being dissipated. And so what we generically do, just to give you some quick illustration, if this is the merger site down here with the two stars and there's some flare propagating out, we do a difference calculation of the pointing. So we put two spheres or two spherical shells around the binary, and we check how much energy in terms of pointing flux is going in, how much energy in terms of pointing flux is going out. This is accounting for the term highlighted in red. And then you can compare this with how much energy is stored in the field configuration, because there could be, you know, some residual change in how the field is aligned there. And once you subtract all of those components off, you get the amount of energy that's being dissipated, because within the formalism that we're using, the energy is literally, you know, going down the drain. We're just removing it. So whenever you get plasmoids, you get a certain amount of dissipation, and this is the way we can estimate that. And that you can use like as an order of magnitude estimate for how much energy is available in that sense to drive radio phenomena this way. And so this is what we did, and back then we were, you know, quite happy to see that we got a very clean linear dissipation. This is what we would expect for a single pulse. Since then we did, this is really work in progress now. Since then we did like some really good improvements on the numerics there and also on the simulation setup. And now what we can show is that, you know, whenever you get this flare, you get this periodic dissipation type event. So if you look at the lower panel, you really see that the luminosity is spiking. This is every time that the plasmoids form. This happens slightly later than the flare because it happens in the trailing current sheet. That's kind of a mechanism that will generalize to all sorts of alignments. I don't have to pick anything out by eye. I can just compute what's the amount of energy dissipated. And it nicely does exactly what we would expect. And so with this, I think I'm right on time for kind of the final interesting case. This is the most exciting thing that we found, because all of that was really nice. But, you know, what happens if I go to even more general cases? What if I say, well, you know, maybe only one of the stars has a strong magnetic field and the other one has a magnetic field that's 100 times or 1,000 times weaker? Do I still see something? Because flaring for this one will kind of be suppressed. But it turns out that the plasmoid mechanism is really, really cool there, because what will happen is the neutron star will sort of act as a perturber in the wind of kind of the orbiting binary. This is a scenario proposed at Columbia recently by Navid Sridhar and Brian Metzger. But different from their analytical estimate, we actually find that because you get some small residual twisting, you can launch a copious amount of plasmoids. And so literally, if you look at that picture, is as the field lines are going around the star, they're driven together by the orbital motion, they start to reconnect, and you get something that looks a bit like a plasmoid laser or so going out. But I'll specify that in a bit more detail. So if you want to look at the same type of picture that we were looking at before, you basically see, again, in terms of twist that is building up, that you're building up a small twist here on the left at the unmagnetized neutron star. You see that you get like these mini flares that propagate along the orbital plane. And now on the verge of the mini flares that happen quite frequently, you get like plasmoid chains propagating out. Kind of same mechanism. Difference is we get way more plasmoids and way more frequently. And so what I'm now going to show you is a not quite straightforward picture. You have to think about this twice. This is why I first show you the cartoon, and then I show you the actual simulation result. And why it's so complicated is entirely on me, because I said earlier, I really like numerical relativity. I like to rotate the space around the stars instead of rotating the stars. So actually what happens is, and what we're going to see is the two stars are fixed. And that means that if I throw something away from the star and it's propagating out, it's not just flying away from me, but it's also flying around me. And so if I produce any plasmoid here, if you think of this like as ballistically throwing a plasmoid out, then the plasmoid will not just go out in terms of radius, but it will also spiral around me as I sit on my star and the world is just rotating around me, quite literally. And so what you can then do is you can put a detector there, and you can actually measure the amount of plasmoids and the amount of luminosity in the plasmoids that is propagating out. So I'm now going to show you kind of our latest movie on that. So when you take a look down here, this is showing you pointing flux on this detector. Again, the detector is rotating with the binary. So you're not just seeing at something that is happening at a fixed location in space, but the thing is actually rotating at a constant speed. On the right here, you see like this residual luminosity is the luminosity of a moving star, because a moving star, just like a rotating pulsar, will also generate pointing flux. So this is what you see over here. And then over the left, the undermagnetized star, it's like the weakly magnetized star, will produce much less emission. So this will be significantly suppressed. And this is why you see more on the right than on the left. But that's not what we're after. What we're after is actually some sort of flaring event at the center. And what you see here, let me just pause that for a second. What you see here is you see this mini flare propagating out. And now in the tail of the mini flare, you get a chain of plasmoids right here, right here. And you actually get a lot of plasmoids. And this is really periodic. And so what this is telling you is that even in the most general case where you would say, you know, the flares are not sufficient by themselves, you basically get this sort of periodic plasmoid emission that's just going on around you. That's like a pinwheel, basically just being ejected in 360 degrees. That still contains enough electromagnetic energy to make up for an interesting phenomenon. Actually, let me play that again, if you didn't get a chance to look at this. So you basically get the flaring event now, then you see there's a trailing sheet of plasmoids, and then this is periodic, you get the next flare, you get the next trailing sheet of plasmoids, so you really get like a constant plasmoid emission from the system in the most general case. And so you can do the same type of analysis I was showing earlier. You can see how much energy is dissipated. It turns out that a significant fraction of the energy, I think it's about 30% or so, is dissipated in the plasmoids. And again, surprisingly, although we don't have enough resolution in the simulation, it's kind of first thing, blah, we have about a periodic flaring that we can identify just associated with the plasmoids. It's a significant fraction of the wind. And so we're looking into this further. This is why I cannot say more at that point, but it looks quite promising. It's kind of an additional effect that we would expect in general, right? Even when the special cases I was showing before would not work. And so kind of as the bottom line for the second half of the talk, I was kind of saying, you know, all of those flaring events are interesting. They might be very hard to detect, and I didn't really discuss with you how probable it is to detect this. We can talk about that later. I talked with some observers who are looking into this. There are even some people from LIGO now thinking about doing some sort of pipeline. I saw it in the literature, and also heard from people that they're thinking about kind of doing like a warning system also for this type of precursor event. I was telling you that one of the mechanisms that could produce that is really the flaring. And this is very interesting because the flaring can boost the emission, so it can boost the power that's available. And then even in the most general case, you can get like the copious emission of plasmoids, which at the end of the day could really produce also coherent radio and X-ray emission, additional to the flaring types when that's not feasible. I think with that, we can conclude the talk. I'm happy to take questions now. I'm happy to take questions later, or whenever I meet you guys at the IS. So, thanks.
Okay, well, thank you. That was there was all sorts of fascinating stuff in there. I think we can take a few questions now, and then more this afternoon. Roman, I think you had your hand up first.
Yes, hi, Elias. Very nice talk, very interesting. When you were talking about this, you know, this in the second part of the talk, my understanding of what you were showing was that you were doing the sort of force-free MHD simulations, right? Of the two.
It's pure force-free, yes.
Yes, but it's MHD, so and it's probably not resistive. So in that case, how were you getting this dissipation? Was it purely dissipation at the numerical level, or?
Okay, so two things. I mean, we're not doing MHD, so there's no fluid. We're literally just doing Maxwell's equations with an effective force-free current. The way that dissipation there works is you compute the difference in the E dot B, and we're doing this implicitly. So the thing is, we actually do have an effective resistivity that we can set, that is set by the specific current that we put. So the first answer is we do have resistivity, and the second thing is, because we are in the plasmoid limit, and this is something I did not mention, in the plasmoid limit, the reconnection rate becomes constant. So if you think about this picture where the field lines were flowing in and they were flowing out, that rate is becoming constant, and it's becoming independent of the Landquist number, and so independent of the resistivity. And so in principle, as soon as you go into that limit, you're sort of fine with the estimate that you're making, because it's not going to change if you go to higher or to lower resistivity, so to speak. But the point that you make is interesting nonetheless. I mean, in principle, with these simulations, we cannot track how much energy you actually have to accelerate particles. For this, you would have to do a peak simulation of the current sheets that you get. But we can still do what we believe in kind of a reliable order of magnitude estimate on the amount of energy you can dissipate.
Okay, thanks.
Good, Carolyn?
Yeah, thanks. This work on the precursors is really interesting to me. I'm wondering, you said you looked at magnetic field differences of up to a factor of 100.
Mm-hmm.
Naively, I would expect for a binary neutron star system that for the first neutron star in the system, you might have some mass transfer onto it. And so you go into this millisecond regime where the magnetic fields might be more like 10 to the 8th Gauss,
Mm-hmm.
in which case you'd have an even larger difference in the magnetic field. Have you thought at all about that?
Yeah, so this is what the second case is about. So the thing is, this flaring event, like this giant flares that you see up here, those would not be feasible in the case, simply because like the twisting, if you think again about the rubber band, I mean, it would thin too much. I mean, you don't get any flare. But the interesting thing is, if the neutron star acts as a perturber in the, let me just go back to this picture because it's more clear. If the neutron star kind of acts as a perturber in the magnetosphere of the orbiting star, and we're not sure yet how much of the flaring you need. I mean, this is like the first thing that we did there. But in principle, if it acts as a perturber and the orbital motion would be enough to drive the reconnection, then this plasmoid thing would still happen. That's the interesting thing about that case, because you would only need one neutron star with strong magnetic fields and the other one wouldn't matter. But we still have to, there were some numerical issues in pushing it further down than a factor of 100, but we're trying to sort it out. Yes, it's a very good point.
Cool, thanks.
Jim?
Yeah, I also had a question about the second part. It was great. You showed at the very beginning of the second part, sort of standard simulation of a pulsar with the current sheet at the equator and the pulsar wind sort of sculpting the magnetic fields into closed regions and open regions. So if you imagine starting the neutron stars off much farther apart, then they would be these two interacting current sheets at the equator. There would be winds, there would be a bow shock, in this particular case of this general unequal magnetic moments, one would be dominant over the other, kind of like colliding stellar winds in massive binaries. And then as they get closer and closer, those winds and current regions must be interacting even more. And in fact, there's a binary pulsar where you can actually see the bow shock from so I just wondered whether any of the, emission or any of those shocks or any of that mess would be detectable. I mean, before the magnetic fields can get close enough to start connecting, before you get within the light cylinder, there must be a mess going on already as these pulsar winds collide. And I just wondered, is that just energetically so much less than what you get by spinning up the magnetic fields when they
this would sort of be my naive answer. I have to admit, I haven't thought about that, about putting them further apart and seeing about that too much. The problem is that the binary pulsars you observe are much closer. For the gravitational wave event, if you think about hundreds of megaparsecs,
to be very early stages, long before they're going to be merging.
Yeah, exactly.
But still, nonetheless, I mean, if you're thinking about precursors, you might be able to associate emission from objects that are not close to emerging yet, but are another so many stellar radii apart from that. I mean, the question is, how early do you begin to be able to detect any kind of interaction?
I guess that really depends on the energetics. Like because the thing is, I mean, the energetics, if they're further apart, and the winds don't have that much kind of overall energy, right? Yeah. So you can see that for nearby systems, but for the systems in the gravitational wave events, I mean, those are further away. So we did do the estimate in terms of how much energy do you need to be observable, even for this case, and it turns out to be really challenging, because even the energy that you have initially in the bow shock, you need to convert that into some observable radiation that typically is like 1,000th or so of what you have available. Right. And so that would then constrain basically the distance of any such phenomenon to be very close to Earth. So that's like not the systems we have considered here, but I agree with you in general, this should happen. I just think that for those systems, we would not be able to see it.
Right. It would still be interesting to estimate the ratio of energy that you get from this plasmoid, from the twisted field lines, compared to the energy you could get from colliding pulsar winds, you know, at larger radii, just to know how much of an enhancement.
If I
Yeah,
may
I think
offer,
that's interesting.
if I may offer a comment on this, I guess the energetics of whatever is happening should be decaying as a distance separation between the two neutron stars to the -6 power, because, you know, for the dipole, you know, for the most favorable case of a dipole, you know, the magnetic field decays as 1/r cubed, and then the energy density would be going as 1/r to the 6. So it you should probably see a lot of activity happening right before the merger and not so much further out.
I mean,
that would be the per volume, right?
Yeah, per volume, yes.
And then you integrate over the interaction region, which is going like r to the squared, I guess, or something. So the total power you can extract is large. Again, it's like colliding stellar winds. You see them even if the stars are far apart, because the interaction area is quite large.
That's true, but I mean, there would still be some decay with a distance.
Absolutely.
And in the case of the double pulsar, we do see certain things happening, certain periodicities and so on, just because we got lucky and we see it almost at dawn, and we just see the eclipses going on in the system. And you know, you're just shining by the beam of one pulsar through the magnetosphere of another. I mean, hoping that we will get lucky for such event in these systems, which are on much larger distances from us, is well, maybe we will. That would be great.
I just want to make a quick comment to Roman's estimate. I mean, the 8 to the -6 is quite good, but it turns out that for this twisting, because the twist also has a power with the radius, it's actually not that bad. It's like we found, like, I think the estimate was like 8 to the -4, and we found 8 to the -7 half of the simulation. So actually for this sort of event close to merger, it's not just as bad. So we get a little bit more. Just a side note I wanted to make.
Okay, well, those who can come back at 2, we can dig further into some of these questions, and let's thank Elias again for a fascinating and wide-ranging talk. So thank you.